everyone, my name is shera.gilbert with matric number AN180197. My supervisor for my final year project is Professor Madya Dr. Andre Kusbiantoro. In this video, I will present my final year project entitled Porosity Analytical 2 based on infrared images of concrete. In these presentations, I will include an abstract, introduction, literature review, methodology, result discussion, and conclusions from my project. First of all, this is my poster for my final year project. Basically, this study proposed to quantify the porosity on infrared images of concrete and correlated porosity of concrete with their characteristic strengths. However, to determine the accuracy of MATLAB software, extra image analysis is conducted using image exposure editing as shown in this video. The MATLAB output was then collected and compared to image exposure editing to determine the relationship between porosity, compressive strength, and thermal diameter reduction rates of concrete. The experimental findings revealed that porosity impacted the thermal diameter reduction rates with a dependable accuracy of 90%, compressive strength of 70%, and concrete density of 60%. Furthermore, the research revealed that concrete with high characteristic strength is less porous, which means it is denser and transfer heat slowly to the surface, lowering the thermal diameter reduction rates value of the concrete. Ladies and gentlemen, porosity is the primary factor that governs the strength of brittle materials like concrete. Porosity measures the volume of the voids in concrete. As the capillary porosity decreases, compressive strength increases. Porosity in concrete can cause many failures to the concrete. For example, spallings on concrete structure as shown in this video. Therefore, to accurately analyze concrete's building stability and durability, the porosity of concrete must be appropriately quantified. Limitations of porosity measurement techniques due to the advanced machinery requirement has initiated the investigations of finding simple image analysis techniques using infrared imaging in this study. A study by Circa and Adderley in 2018 has proven that the infrared thermography detection defect generally corresponded to non-visible defects, and appear that infrared methods have a very low chance of false identifications. Ladies and gentlemen, Saifuddin has investigated the concrete porosity using ASTM saturation technique. There are three ASTM saturation techniques, namely vacuum saturations, boiling, and water saturations. In his study, he concludes that water penetration into concrete pores is higher under vacuum saturations than cold and boiling water saturations. According to Merhofer in 2018, porous mixes have higher heat conductivity and hence have a better probability of detecting faults in concrete. Lastly, Ralinska in 2018 used image analysis where a digital image was taken of each face then was processed using Adobe Photoshop software. Afterwards, the image was converted into a binary image and pores was calculated as shown in this video. The result was then obtained in different picture editing methods using MATLAB software and image exposure editing in order to determine the correlation between thermal diameter reduction rates of concrete with porosity. The graph shows that porosity affected the concrete's thermal diameter reduction rates, where the porosity increased with 14.2% and thermal diameter reduction rates also increased by 0.029 mm per second. However, this study has three outliers since the data did not fit the rest, including 9.52%, 11.66%, and 12.23%. It may due to specimen error even all precautions were taken, including consistency in producing the specimen. Although this analysis causes unusual data, it has proven that porosity affected the concrete's thermal diameter reduction rates. However, image analysis using image exposure analysis show that accuracy only 0.004, which is likely more inaccurate than the MATLAB image processing method. The result was then obtained in different picture editing methods using MATLAB software and image exposure editing in order to determine the correlation between thermal diameter reduction rates of concrete with porosity. The graph shows that porosity affected the concrete's thermal diameter reduction rates, where the porosity increased with 14.2% and thermal diameter reduction rates also increased by 0.029 mm per second. However, this study has 3 outliers since the data did not fit the rest, including 9.52%, 11.66% and 12.23%. It may due to specimen error even all precautions were taken, including consistency in producing the specimen. Although this analysis causes unusual data, it has proven that porosity affected the concrete's thermal diameter reduction rates. However, image analysis using image exposure analysis show that accuracy only 0.004, which is likely more inaccurate than the MATLAB image processing method. Last but not least, the relationship between porosity and compressive strength was also determined, where the graph showed that concrete porosity decreased as compressive strength increased. For example, the concrete with a strength of 19.56 megapascal has a maximum porosity value of 14.2% with coefficients of 0.675. It demonstrates that high-strength concrete has less porosity than low-strength concrete. As a conclusion, this study has successfully achieved the objective of this study, where the results show that porosity affected the thermal diameter reduction rates with a reliable accuracy of 80% and 90% between thermal diameter reduction rates with compressive strengths. The thermal diameter reduction rate trend also demonstrates that concrete with a high characteristic strength is less porous, which means it is denser and conducts heat slowly to the surface, giving the concrete a low thermal diameter reduction rates value. As for recommendations, other software could be used to analyze the porosity of concrete and point heat to concrete surface instead of surrounding heat could be used to provide infrared image data.